The main focus of this skill is to take a deeper dive into the Thevenin equivalent circuit as a tool. We kind of touched on this briefly when we were talking about the reflection and transmission coefficient, and let's just start by taking a deeper look. And in general, the purpose of this is to convert an incoming wave in the transmission line. So this could be, say, a V plus on the generator side, on the load side, or V minus on the generator side. And the main goal is to convert that into the actual voltage that you'll see outside of the transmission line. So in the case of V plus, this is converting from V plus to the voltage at the load, or in the case of a reflected wave, it would be the connecting V minus to VG. And this could be V plus plus or V plus plus plus, but the main thing is you have a certain value of the traveling wave that's going through the transmission line, and you want to figure out how that translates into the actual component that's immediately outside of the transmission line. So I'm going to start out with reviewing our earlier version of how we came up with it, and then we'll kind of strengthen our understanding of that theory by looking at a different way to derive it, both on the generator end and on the load end. So let's call this the transmission formula approach. So this is how I introduced it in the beginning, but let's just speak very generally. We have a transmission line, and then it's going out to a load, and you want to find out what this voltage at the load is, but this could be the generator, but just whatever is immediately outside the transmission line. And the transmission line has a characteristic impedance of Z0, and then you have some kind of input wave. We'll just call this, since this looks like it's on the load side, we'll just call this V plus. But it can just be any wave that's traveling towards your target over here. Now, what we remember is from previous discussions is that a portion of it will reflect. So one of the key things that you can calculate is gamma, which is going to be new minus old, so ZL minus Z0 over ZL plus Z0. And to convert this wave that's traveling to the right over to this voltage over here, if you wanted to find out what the reflection is going to be equal to the incoming wave times the reflection coefficient, which is why it's called the reflection coefficient. But if you want to find the voltage at the load, we also found previously that the equivalent of, it's going to be equal to V plus V minus plus the reflected wave, right? So V plus V minus, but since this is V minus is gamma V plus, so we can also find that the voltage at the load is going to be equal to, if you write it in terms of V plus, it's going to be equal to 1 plus gamma V plus. So we also define this quantity here, which we'll call the transmission coefficient, and the transmission coefficient is 1 plus the reflection coefficient. So if we take another closer look at that, let's just write that out in terms of impedances. So 1 plus gamma is going to be equal to 1 plus new minus old over new plus old. And let's whip out our algebra skills and put this all into single fractions. So the 1 is going to be ZL plus Z0, and then plus ZL minus Z0, ZL minus Z0, right? Which is going to end up giving you these, the Z0s will cancel, so you'll end up with 2ZL over ZL plus Z0. So let's plug that into here. You now have VL is equal to 2ZL. So let's just do a little bit of reordering. We're going to put the 2 here, and then we have our V plus, and then we're going to put the rest of this out. ZL over ZL plus Z0. So if you look at this formula on the face value, this looks like a voltage divider where you have this, we'll call this the Thevenin equivalent voltage. And it's a voltage divider between ZL and Z0. And then this will be the voltage of the load. mean to put that there. And so if you want to call this, so what we do is we can designate this as the Thevenin equivalent generator and the equivalent source impedance. You can substitute the transmission line on the load end with this circuit here, where Vt is going to be equal to 2V plus. So again, what that means is if I know what the incoming wave is and I want to know what that looks like to this load, I just recreate this chunk of the circuit here with this piece here, where I pretend like it's a generator with a voltage value of 2V plus, so double the voltage that's coming in, and then I pretend like it has a source impedance of Z naught. And then if I just then use Kirchhoff's voltage law to solve for it, I will come up with the correct output. And so this circuit here that I've outlined in blue is the Thevenin equivalent. Let's drive home this theory some more by just deriving it from a different approach. So we'll just say the load and derivation. So let's just start out again. Let's just start out by drawing out our goal. Our goal is to find a Vt and a Zt such that this circuit that you see here, this Thevenin equivalent circuit here, is equivalent to what you'll see in the transmission line. Where if you just solve for this circuit, your resulting VL that you solve for here will be equal to the VL that this transmission line will see. Let's start out with our simple truths. Now, mathematically, this is very, very similar, equivalent to the derivation that I did above. But I think that showing it a few different ways helps you internalize the end result. So let's just write down the basic facts that we know at the load end. So the first thing is that the voltage at the load will be equal to the sum of the incident wave and the reflected wave. And the other thing that we know is that the current at the load is going to be equal to the incoming current and the reflected current. So the incoming current is going to be equal to V plus divided by Z naught, and then the reflected current is just simply going to be V minus divided by Z naught because of Ohm's law, right? That would be a no, don't forget. You have to put in that negative sign because the wave is traveling to the left, or else you will make me very sad. I cannot repeat this enough. All right, so this gives us two equations. Now, actually, before I call that equation 2, let's just manipulate that a little bit so that it looks closer to what we want. Let's just multiply both sides of the equation by by Z naught. So if we multiply both sides by Z naught, we now have V plus minus V minus is equal to IL Z naught. And we'll call that our equation 2. So now, if we want, remember our end goal is to find out what VL is in terms of V plus, the wave that's exiting the transmission line. So in that case, if what we want is V plus, we'll just add the two equations because that way the V minuses will cancel out, and you'll end up with 2V plus is equal to VL plus IL Z naught. So now let's call this equation 3, and we're going to go back and compare that with what the solution to our Thevenin equivalent circuit would look like. So if we just look at this circuit, the Thevenin equivalent voltage is going to be equal to the voltage drop across this ZT, which is going to be equal to IL ZT, because we know the current across this is going to be the same as the load current, and then plus VL, this VL over here. So then we'll call this equation 4. If we reorder this and compare, we have this VL over here, and you also have your VL over here. You also have this term here, which matches this term here. And then finally, you also have your 2V plus and your VT. So by comparison, by comparing 3 and 4, you'll find that VT is going to be equal to 2V plus, and ZT is simply going to be equal to Z naught. Now let's conclude by running this again and seeing what it looks like on the generator end. And the main goal of this is just so that you can see, you can run through this derivation with a wave that's traveling to the left-hand side. Not necessarily to a generator, but just exiting the transmission line to the left-hand side and seeing how that changes the derivation. So on a generator end, the main difference compared to what we had before is that instead of before, when you were trying to connect a V plus to a VL, now we're trying to connect a negative going wave to Vn, so the incoming end of a transmission line. So remember our transmission line going here, basically the voltage drop at the output we were calling VL, the voltage drop at the input we're calling Vn, right? So we're trying to connect, you have a V minus going that way, you have a V plus going that way. Before we were connecting V plus to V load, now we're trying to connect V minus to Vn. Now our process is going to be very similar. Let's just start with what we think we want the equivalent circuit to look like. So the equivalent circuit in this case for the leftward going wave is we're going to have our Thevenin equivalent, generator and source impedance. This is going to model the transmission line at the left-hand exit. And then at the output, we're going to have our Vn. So let's just start with a different order here. Let's just start by solving the Thevenin equivalent circuit here first. So if we look at that, our V Thevenin equivalent is going to be equal to Vn, this potential here, minus the potential drop across this ZT, which is also going to be the current going in. So In times ZT. So that's going to be, just to keep the same numbering, this is going to be our equivalent of equation 4. Now we go back to the input side. We know that the input voltage is still going to be the sum of the wave, the voltages going in either direction. That's going to add up to this input voltage. And then the same thing with the input current. It's going to be equal to the input current going in the right-hand direction and the input current going in the left-hand direction. You do that by dividing by Z naught, but remember to change the sign for the leftward direction, and that's going to be equal to your In. So 1, and then this one, let's do the same reorganization, multiply both sides by Z naught in Z naught. So this is the same equation as what we had before. Actually, what I meant to do is make this equation 2. The only difference is because now we're trying to connect the leftward going V minus wave to Vn. We want to take out the V plus. So instead of adding the two equations, we will now subtract the two. So if we subtract 2 and 3, now we're going to have 2V minus is going to be equal to Vn minus I in Z naught. And so now, once again, let's do our comparison. We have this 2V naught over here, 2V minus over here. That matches up with this. If we look at our V load, those are the same over here, which leaves this term here matching that term. So you can arrive at very similar conclusions, where Vt is going to be equal to 2V minus, and your equivalent impedance Zt is going to be equal to Z naught. So again, that tells you basically the same principle is if you have a wave that's exiting the transmission line and you want to know what that looks like to whatever's outside of that transmission line. So it doesn't matter the direction, as long as the direction is exiting the transmission line. What you do is you draw the equivalent circuit, which is a source that is equal to 2 times the voltage wave that's going in this exiting direction, and then having a source impedance equal to the characteristic impedance of the transmission line. And then once you solve the circuit, the output will basically tell you what this load sees as a result of that voltage wave that's exiting the transmission line.